Okay, let's go ahead and get started. I'm surprised. What we talked about, these ones, this would have been Friday. Was started into electrodynamics. Style it in, folks. We talked about electrodynamics, moving electric charges. We talked about the electric circuit, just somewhat. That's the major part of this chapter that got cut out. Was we used to really have to study the electric circuit and work on Ohm's law for every part of the electric circuit, which is just way too much. I agree that should have come off the registry, and therefore it should have come out of the textbook. So, but we talked about the components of an electric circuit. So what we had to have to allow electrons to flow predictably, so that we could use them, was a conductor. But to avoid short circuits, to prevent the electricity from going where we didn't want it to go, we had to have insulators to kind of keep them inside. We talked about what a semiconductor was, and we're going to talk a lot more about semiconductors later on and how they actually work. But a semiconductor is something that sometimes acts like an insulator, sometimes it acts like a conductor. So sometimes it allows electricity to flow, sometimes it stops electricity from flowing. Then we talked about a superconductor and what superconductors were and where we actually use those in medical imaging. A superconductor is a very efficient conductor. So it's material with a lot of valence electrons, and the electrons flow very easily. But still, we have the same problems that we have anytime we have electric flow, and that is that we create heat, which increases resistance, which increases heat, which increases resistance, and so on. And that's basically how your ovens work, your electric heaters work, and everything else that generates heat that we want to use works. So naturally, for a superconductor, not only did we have to have something that was a very good conductor, but we also had to keep it very cold to minimize that resistance. We talked in the previous lecture about what an electric ground is, and for a circuit to work, we had to have an electric ground. So those were our electric circuits. We talked about Ohm's law. That is V equals IR, and we talk about what happens if you change one of those components. If you change intensity and you don't change resistance, then voltage is going to increase. If you increase resistance, you don't change intensity, again, voltage is going to increase. But if you want to maintain the same voltage, then intensity and resistance would have to be inversely proportional. Then we talk about the two different types of current that we have. And from batteries, we get alternating current, and that's current that goes back and forth, kind of in a sine wave, right? So it goes in, it comes out, it goes in, it comes out. And I'm sorry, I said direct current, and then I described alternating current. Direct current comes from batteries, and it goes in one direction until the supply of electrons is depleted, like your phone, right? Your phone, the longer you use it, the more it wears down. So that comes from batteries. Direct current comes from batteries. We do have direct current generators, but really the function of the generator remains the same. It's just how the output comes off of it. So we can get direct current from a generator, but most of the time we're using generators. We get alternating current. Alternating current goes in and out, in and out, in and out. So in the United States, that happens 60 times per second. And when we get into exposure timers later in the semester, we'll drum that back up. The one thing that we didn't talk about is electric power. And electric power is just a mathematical equation that tells us how much power, how much work we can do with electricity. And that's just calculated as power is equal to intensity times voltage. So the two components of electricity, voltage, your potential times your amperage, is what gives us our electric power, and that is measured in watts. If you look at the top of your light bulb or whatever, It tells you what your wattage is. It's a little bit more confusing now with our LED light bulbs. It gives us a wattage, and then it gives us an equivalent wattage to what that would mean if you had an incandescent light bulb. So LEDs use a whole lot less electricity. So LED that uses 5 watts may be the same as an incandescent light bulb. The incandescent light bulb, when I say incandescent light bulb, that's a light bulb with a filament in it. So it may use the same amount of wattage as a 60 watt, or I'm sorry, put out the same amount of light as a 60 watt, but it only uses 5 watts of power. So that's what that's all about. So today, what we're going to talk. Any questions on all that? For electric power, yeah, power is just intensity times voltage. So it's kVp or voltage times amperage.
When you talk about alternating current, you say it goes in and out, in and out, in and out of what?
Yeah. Okay. So you got a wire, right? And the electricity. Let's say your wall is here. You got an extension cord going to your toaster. Oh, you got one of those 2-slice toasters. So the electricity is actually going through the wire in one direction, and it goes back to the wire in the opposite direction. Yeah. So it goes in and out of the wall.
Is that also just indirect current?
Indirect current. I guess you could, use alternating and indirect kind of interchangeably. Where are you pulling indirect?
Well, that was talking about like your tube and everything. Like you use like going from the transformer all the way into the hospital is all indirect until you get the extra tube is direct.
Oh, yeah. So yes, and that's we need the alternating current. So if you if the terminology on the test is going to be alternating, but yeah, we want alternating current all the way up to the X-ray tube, and then we want direct current going across the X-ray tube. Yeah.
Is that part you'll be on the test too with the X-ray tube?
Yes, probably, because we're going to go through the electric circuit. We're not going to get there today, but we're going to go through the electric circuit for today's was this Friday. We'll probably finish up chapter on Friday, and then any questions that y'all might have on Wednesday before we press on into the next section, we'll address those. But yes, because we have to have the alternating current all the way up to the point of the X-ray tube, the direct current through the X-ray tube will probably be on test.
So then our test is on Wednesday, right?
Our test is going to be next Friday. So yeah, so a week from because y'all have patient care on Tuesday or not Tuesday, Wednesday. Yeah, so we'll do our test on Friday. So we'll finish up probably this Friday. We'll if you have any questions, we'll work through those on Wednesday, and we'll start chapter 6 on Wednesday, and then we'll have a test on Friday. Test though is just going to be out of this chapter, with a possible exception of current through the X-ray tube. Any other questions? Okay, then what we're going to talk about today is magnetism. So we're going to go up to page 84. I'm going to stop at electromagnetism, and that will be our lecture on Friday. So we'll tie together, electricity, magnetism, how we create the transformations that we need in both the auto transformer, step up, step down transformer, both rheostats, and how it is that we manipulate. We use electricity to create magnetism, and we manipulate the voltage and the amperage so that we get what we want, so that we can have a predictable exposure on the patient, both in the penetration and the quantity of X-rays we're going to create. So that'll be our lecture on Friday. So it's going to be kind of a heavy lecture, so be ready for that. We're going to try to finish up. If we don't finish up, then we'll finish it up next Wednesday before we'll talk about a review. All right. So magnetism. A lot of this is going to sound awfully familiar because, some of the properties and principles of magnetism are the same as properties and principles of electricity. So, with magnetism, just brief history of it, and you can look this up. This is really kind of legendary. It's, we don't know for sure exactly where magnetism was first noticed. So it's discovery, not an invention, but a discovery. But as the story goes, there was a shepherd in a portion of Greece, and his name was Magnus. And conveniently enough, he was living in Magnesia, portion of Greece, and he noticed that on his sandals, they wore sandals back there, and they're hammered together with nails. He noticed that some uh, metal shavings were sticking to the bottom of what looked like metal shavings were sticking to the bottom of his sandal. So he knew something was going on, something weird was going on. We have a similar situation here in East Texas. You ever walked across say, a red clay area that was sort of wet? What happens at the bottom of your shoe? If it's a big enough field, you're taller by the time you get to one side than you were before you started, right? So you're walking along and you just pick up clay. Well, kind of the same thing here, except for it was metal and it was sticking specifically to the nails and not to the entire bottom of the shoe or sandal, whatever it was. So he realized, and again, this is legend. We don't know if this is actually how it happened, but that's the story. Now, Bushong's a character. He's a funny guy. I don't know that he still does lectures, but if he does, if he comes back through the area, and he usually goes to either UT out on 271, or he goes to Mother Francis and I forget what the room is, their conference room, and he'll give a lecture. And it's worth going to. Brilliant man, but he's getting pretty old, so I don't know that he still lectures. But so because he's a character, he throws some stuff, into the textbook sometimes needs to be taken with a grain of salt. The cows in Magnesia didn't really give out laxatives. Okay, it was milk from the Magnesia area of Greece. So it was milk of magnesia, but it wasn't milk of magnesia like what you buy in the store. Okay. So again, grain of salt, he's a funny guy. But it just doesn't come through sometimes in the text. So that's a historical what we believe might be the historical context for how it is magnetism was discovered. But what we know about magnetism, what you know about magnetism, is very easily to observe. And that is, you take a couple of magnets and you can stick them together, or they'll stick to something, right? They'll stick to something that's attracted to magnets. What we also know is that you can take them and you can kind of put them to where they face each other in a certain way, and they tend to push each other apart, and in other ways they pull each other together, right? So what we know is that they have two poles. They have a north pole and a south pole. We also know that magnetism goes through the earth. That is why if you have a compass, the needle of the compass is going to point towards the north pole. What we also know about magnets is that those poles, what we have is in those poles, let's say we've got a north pole here and a south pole here, and that's just perceptional. I mean, who's to say that, the guy who first described magnets didn't have it backwards and you flip it around, right? So it's just perceptional. But what we do know is that in the perception that we have of magnets, and how we describe magnets, is the magnetic field lines go around and they reach out from the center of the magnet three-dimensionally. So I can only draw two-dimensionally here, but they're going all around the magnet, right? So, and as they go around the magnet, what we know is that the magnetic field lines enter the north end and exit through the south end. All right. So, and it becomes so profound that if you were to take a magnet a compass, I'm sorry, and you were to approach the North Pole, what you would find is that it will become wildly inaccurate. And that is because here, what we're following, let's turn this into a globe instead of into a big square magnet. If you're standing right here and you've got your compass in your hand, it's going to be pointing towards the North Pole, right? But the closer you get to the North Pole, now you're up here, then your compass is going to be trying to point instead of towards the North Pole. Well, it's still going to be trying to point towards the North Pole. It's just that now the North Pole, you're standing on top of. Okay. So those magnetic field lines fold into the earth and they exit out of the south end. And if you, I don't know if they still make these or not, but when I was a kid, these were fascinating to me anyway. They had a compass that you could put on the hood, not on the hood, but on the dashboard of your car that was kind of floating, right? And if you hit a bump or you're going uphill or downhill, it'd kind of shift around. So if you had one of those and you got close to the North Pole, it'd have a tendency to point into the earth. And if you were getting close to the South Pole, it'd point straight up to the sky. Okay. So those magnetic field lines are not static. They're moving through and they have definite characteristics. So your magnets that you hold in your hand have those same properties as well. Those magnetic field lines are going in the north end of the magnet, coming out of the south end of the magnet. Okay. Everybody good with that so far? They're invisible. They're not as easy to detect as electricity. You know, electricity, we're going to draw a lot of commonality between electricity and the magnetic field lines. But the field lines are not easy to detect. You have to have something in order to detect them. You got to have a compass. You got to have something, if only a piece of metal. What do you have to detect electricity? I kind of told on myself the other day, right? What did I have? My skin, right? So you can detect electricity without anything, but magnetism, you have to have something to detect it. Not only do you have to have something to detect it, but you have to have enough of it to be detected. And what I mean by that is imagine every magnet that you've ever seen, every magnet that exists, all right? So the magnetic field lines that come out of a magnet reach out infinitely. Okay, so if I had a magnet situated right here, we got magnetic field lines, and let's say it's a very strong magnet. We have magnetic field lines going through this magnet, just like that one over there. But what we would also find is that if we could had a something that could detect some tripping over my words today, something that could detect the magnetism. What we would find is that if we didn't have this one here that would interfere with magnetism out of that one, we could detect magnetism off of that magnet all the way over here. And if I go to the edge of that one over there, same thing. It doesn't end, it reaches out infinite. So the magnetism of the Earth is really a weak magnetic field compared to, let's say a MRI magnet. But the magnetism of the Earth reaches out into space infinitely. All right. So what that means is that for the amount of magnetism you get off of a magnet, there is no minimum amount of magnetism. Okay. So with electricity, the minimum amount of electricity you get is off of one electron. Right. But what's the minimum amount of magnetism? It's infinite. There is no minimum. Right. Now there's a minimum amount of magnetism we can have initially, but the magnetism that's reaching off of that magnet isn't infinite. So there's no minimum amount of magnetism. So we'll talk a little bit more about that and what I mean by that here in just a second. So where electricity and magnetism intersect is that anytime we send electricity through a circuit, if we have a charged particle in motion, we have magnetism. We create the heat, if we're talking about electric circuits and we send electrons through a wire, we're gonna create the heat that we talked about before, but we're also gonna have a magnetic field too. We're gonna talk more about that on Friday, but for right now, you just need to understand charged particle in motion. Electrons are charged particles. Charged particle in motion creates the heat, but it also creates magnetism. Okay? So now, what is an atom? Yeah, smallest unit of something, right? So what's an atom made of? Protons, neutrons, and electrons, right? So what are the electrons doing? They're orbiting the nucleus. So is an electron a charged particle?
Yes.
It is. It is. It's a charged particle. It has a negative charge. So as it's revolving around the nucleus, it's also creating a magnetic field. Okay, so it's not enough of a magnetic field that you can measure. All right, so it's a very, very small amount of magnetism, but the magnetism is still there because it's a charged particle in motion. So you're going to have a question on the test that's going to ask you what's the minimum amount of magnetism that you can create or that can be created, and that would be the amount of magnetism coming off of a single electron orbiting a nucleus, right? You've got that magnetism, but that magnetism reaches out infinitely. So the minimum amount that can be created is that comes off of one electron orbiting a nucleus or one electron going through a circuit. But what's the minimum amount of magnetism? It's infinite. There is none. There is none. Okay, so you see the difference between those two?
The minimum we can make is the electron.
The minimum, yeah, that can be created is the magnetism that will come off of one moving electron, one moving particle. But in that magnetism, since it reaches out infinitely, there's no minimum amount of magnetism. Okay, so two questions there. You got one question asking how much is the minimum that we can create or can be created naturally, even. That's off of one electron. But the minimum unit of magnetism doesn't exist. It goes on forever. Okay, so the catch here, and there's always a catch, is that if we have an atom that has one electron, then it's going to create a magnetic field. Okay, so what do we have here? We have one electron, and it's a neutral atom. We have one proton. We have, what's that? It's hydrogen, right? So if, though, we change this into helium and we have two electrons, then what we get is, because of the magnetic fields that are created in both of these, and we've got two different things going on, we've got what we call electron spin, but they're also revolving around the atom, right? So we've got a lot of stuff going on there. If we have two of them together, they cancel each other out. Okay? So if we have an atom that has an odd number of electrons, then we're going to demonstrate magnetism. It might not be a magnetism we can detect because, what are you made of? It's the most abundant molecule in your body. Okay, we're carbon-based, right? And we say that we're full of water, right? So what's water? Hydrogen and oxygen, right? So the most abundant thing in your body is going to be that hydrogen. So why are you not magnetic? Okay, the hydrogen does. The water does not necessarily, but the hydrogen does, and we're going to get to the little bit more of that here in a second. But if we were just all hydrogen, we still wouldn't show a magnetic property. And that is because those things are likewise going to be oriented. If we had a collection of hydrogen, it's not going to just be a strong magnet. They're going to be oriented okay, so let me do this. let's say we have two hydrogen atoms side by side. How many electrons do I have now? Two. So again, they're going to have a tendency to cancel each other out. So just because I have one hydrogen atom, I got one hydrogen atom, I've got a very small magnet. I put two of them close enough together and it screws everything up. Okay. So the key to magnetism in a in a molecule is that it has to have an odd number of electrons. Okay, here's the word that you need to be watching for. In order for an atom to be to demonstrate magnetic property, it has to have unpaired electrons. So what is pair? What is a pair? Two. How many shoes do you wear? Two. What do you call that? A pair of shoes, right? So any atom that has an even number, that's the key, it has an even number of electrons, does not show a magnetic property, but if it has an odd number, it does. Okay, yep.
But if it has an odd number, but there's a second one,
And it
also
may cancel it.
okay.
Yeah. And not that, but not necessarily.
Oh, well, why would we ask?
Why? Why would we not think so? Okay. Okay. So, and this is going off script here.
It's okay.
I mean, we were going to get here, but we're here now. So,
Okay.
all right. So, anybody ever worked a power drill? Okay. Okay. So you put you work in a power drill and you're either drilling through metal or you're working a power drill to drill or to screw in a screw. Right? But you don't have enough pressure on it. If you're screwing in the screw or if you're starting to get into the metal, you don't have enough pressure. Let's start with the screw thing. So you don't have enough pressure on the drill and that drill bit hops out of the slots in the drill. What happens? Yeah, you strip it, right? So not only does it slip out and it doesn't screw in, but what you've taken is, let's say it's a Phillips head. That's a Phillips head, screwdriver and a screw that just has that, two slots. So what happens is it takes some of the metal off of each one of these. So, if you're working with your dad and he says, go get him a Phillips head screwdriver, that's what he's talking about. If he says flathead, that's what he's talking about. All right. Just so you don't get shouted at, that's what he's talking about. Is the Phillips has that, and then Torx bits and all that kind of stuff. You're just going to have to study on your own. But what happens is if you don't have enough pressure on your drill, then it strips it out, right? So it takes some of that metal off of there, but then you pick your drill up and you look at the screwdriver bit that's inside of your drill. What do you see? Little pieces of that are stuck on it. You shake it all you want to, but they're not coming off. And that is because you've taken all these things that were arranged randomly, and by beating on them enough, they start to line up. All right, so let's say we've got two hydrogen molecules and we've got them facing like that. They're going to cancel each other out. But if they're both facing the same direction, even though there's two of them, then and those things may be in sync, then we might have double the magnetic moment, so to speak. Double the magnetic moment gives us magnetic domain, and it gives us a bigger, stronger magnet. Okay? So what this means is you just beat the snot out of your Phillips head screw, and the tip now of your drill bit, or either the drill bit or the screwdriver bit, is now magnetic because you lined all these things up. Happens in blacksmith shops too. A blacksmith may buy a brand new hammer a year from now because he's been beating on hot metal for a year. What'll happen is a lot of those non-magnetic atoms inside of the hammer will line up and create a magnetic property inside that hammer. They say that property can get strong enough that it can reach up with that hammer. If he's hanging, let's say he's making horseshoes, he's got them on the rafter above him, he can reach up and use that to get the horseshoes down. Strong enough magnet that it could pick up a horseshoe. Ever picked up a horseshoe? They're not heavy, but they're not light. You know, I mean, you're not going to pick one up with your refrigerator magnet, right? So it's pretty significant. So you can create magnetism by aligning, and we're going to get here anyway, but by aligning your atoms that demonstrate magnetic properties, you can align, if you get them aligned enough, they can demonstrate magnetic properties and become magnetic. You can create a magnet out of something that is not magnetic. Yeah.
Just something can create a magnetic field doesn't because it's magnetic. Right?
Just because something's in a magnetic field does not mean it's magnetic.
Atoms that just because they can create a magnetic field doesn't make them magnetic.
Yeah, it doesn't if you have a compound of something that might have unpaired electrons, it does not necessarily mean that you're truly going to have a magnet there. Each individual one does demonstrate some magnetism, a small amount of magnetism, but just having a collection of them is not necessarily going to make it magnetic. Yeah.
So right there where you were talking about, it's like when it talks about in the book about the ferromagnetic, like when you bring
We're going completely off script. Yeah, go ahead, because we're gonna go there too.
Yeah, it's like you bring iron to a magnet, now the iron is magnet, but if you put enough heat, it turns into like a forever magnet.
I don't know that the heat itself is going to make that happen. But yes, you can make, through a process of aligning your magnetic domains, you can take something that is susceptible to becoming a magnet. It's not to be confused with susceptibility. He talks about that in the book. That's a penguin you don't need, by the way. But he's got it in the book as a penguin. But by aligning those, it can become magnetic. Whether or not it has to be hot, I don't know. I've never truly looked into what the process is there. All I know is I've screwed up a lot of screws, and I've screwed up a lot of screwdriver bits. And the new screws with instead of having, that's poor representation, but instead of having just two slots or one slot, much better. Much better. The new decking screws that you have now, Torx bits and things like that. Okay. Let me figure out where. Oh, yeah. So going back to hydrogen. So since we've got hydrogen, and since we're talking about ferromagnetic material, if you put something that demonstrates some sort of magnetic property close to a magnet, what do you get? Like ferromagnetic material. You put a magnet close to a piece of iron, what do you get? Connection, right? They're going to smack into each other and they're going to hold on to each other. And the type of material we call that is ferromagnetic. So iron is ferromagnetic, right? So iron will take those magnetic field lines, and this is truly susceptibility, permeability, the penguins he describes in there. It'll take those magnetic field lines and it will direct the magnetic field through that iron. So let's say we've got a magnet here, positive, negative end, north, south, doesn't matter. And then we take another thing, let's say, to keep them straight, it's a ball, a big chunk of iron. You put it close enough to it, those magnetic field lines that are reaching out. Remember, it's infinite, so it is pulling on this thing. It's just not pulling as hard. Then those magnetic field lines will reach out and go into that piece of ferromagnetic material. So if we remove that, let's get rid of that for a second. Let's say our magnetic field lines look something like this, just in its natural state. And then we bring that thing back. Then these field lines are definitely going to go through it, and these might reach out a little bit further. So what happens is that ferromagnetic material draws in those lines and creates a magnetic field in that. Right? That's why whenever you take a magnet and you dip it into a couple of paper clips, what happens?
They all stick to them.
They all stick to it. Yeah. So not only do they stick to, the paper clip stick to the magnet, but another paper clip will stick to the paper clip, right? So that becomes magnetic. So if we take a paper clip would look something like that. It would stick to the other side of that, even though it's away from the magnetic field.
So does the iron itself have magnetic field, or just the one that's being?
It does now because it's in the influence of the magnet. It does then because it's drawn in those lines and it becomes magnetic. So if I move it far enough away, it's not going to demonstrate that. Paperclip will fall off of it.
But like if you had a strong enough magnet, you can go on for a long time.
Yeah, yeah. And I've got magnets in my office I meant to bring, and they're pretty strong magnets just to demonstrate how, how close you can get before, one magnet will move towards the other. That's the problem with being in this room is that, I've got all my props up in 250. And I bring them down here, but, other programs use this room too. So, I can't really take over the room. All right, so this kind of describes the penguins that I was talking about: permeability, susceptibility, the likelihood of drawing in fields of magnetism, and whether or not something becomes magnetic. So that's what those two penguins mean. Even though that's not something you need to hang on to for the registry. But back to hydrogen and what you're made of, and that is, primarily hydrogen, oxygen, carbon, magnesium, calcium in your bones. You got a lot of stuff, but you got a lot of hydrogen. So hydrogen has one proton, which means it has one electron, right? So if you were to put you into a strong enough magnetic field, then you're going to have this same situation kind of going on. So if we put you inside an MRI magnet, which is a superconducting magnet, it is, maybe as much, your higher end magnets, maybe as much as 10 times the magnetic force of the Earth. Very, very strong magnet will put you inside of that. Then what's going to happen is basically what we had going on with the screwdriver. Okay, all of your hydrogen molecules in your body are randomly oriented. Okay, not one of these is strong enough to kind of direct everything in one direction. But if they put you inside of the magnet, what's going to happen is that your hydrogen atoms are going to have a tendency to line up with or against the magnetic field. So they're going to have a tendency to go this way. So they put you into the magnet, and now your magnetic domains are all facing, towards your head or towards your feet. Okay. So what happens whenever we create an MRI image is we've got that going on. So we've taken all your magnetic fields and we've lined them up with the magnetic field in the magnet. And then they send radio frequency in. Anybody had an MRI? I think I asked this question once before. Okay, all that banging around. I'll explain that in the next section on Friday. But it's basically because of the superconducting magnet and what we're doing inside of the superconducting magnet, changing the direction of the current, but also what you have are radio frequency waves that are coming in. They're smacking all your electrons, smacking all your atoms, rather. So it's almost like setting off a bomb, right? So you got all your atoms lined up in one of two directions. And then we hit it with radio frequency, and all of them just slam into one direction, essentially. Now, what type of tissues do you have that have the most amount of water in them in your body? Soft tissues, right? What has the least amount? Bone. Okay. So we're just going to talk about those two first. So what's going to happen is that, you still have hydrogen in your bone, just not as much, right? So what happens is, again, we hit it with radio frequency. They reorient, according to the direction of the radio frequency. And then depending on how much how much hydrogen in the composition of the tissue type, they're going to reorient with that magnetic field at a different rate. Okay. So bone not having much might slam back pretty quick, right? And then soft tissue may come back a little bit slower. And as it comes back, it's going to release that radio frequency back into the atmosphere. And antennas pick that up. This is not on the test, by the way, but the antennas pick that up, feed it into the computer, and depending on the rate of relaxation of those molecules coming back into alignment with magnetic field, we can determine what type of tissue it is and create an image off of that, right? So have you ever seen an MRI? What do you see real well on MRI? The images.
Tissue and
Soft tissue. What do you not see very well?
bone.
Bone, right? So the more water you have, or the difference in water composition between the different tissue types, gives you a different appearance in those tissue types. Beautiful images, absolutely beautiful images. Almost look like paintings or drawings of, the patient's brain or whatever. Bone, you just don't see much of anything. But the soft tissue, because of the hydrogen content, soft tissue images are just outstanding. And it's all, again, because you got hydrogen, unpaired electrons, highly influenced by a strong magnetic field, and then the radio frequency, and anyway, that's MRI 101. So MRI doesn't use any kind of electromagnetic radiation. Yes, it does. Yes, it does. It doesn't use ionizing radiation. It still uses electromagnetic radiation because of radio frequency, right? But doesn't use ionizing radiation. Okay, so now I got to make sense of where we've been and what my notes say. Okay, so the lines of magnetism don't end, they reach out endlessly. So the two things, smallest magnet would be what's coming off of one single electron, but there's no smallest unit of magnetism because they reach out infinitely. You got a magnetic dipole is, north and south. You get enough of them together, you get a magnetic domain, magnetic permeability. We talked about that, the likelihood of, or the ability to draw in those magnetic field lines. Okay, here we go. New material. So we have two different classifications of magnets. And within those two classifications, we have further classifications as well. Okay. So we have permanent magnets and we have temporary magnets. So a permanent magnet will be like your lodestone, right? Lodestone being a natural magnet, which pull out of the ground, it's already magnetic. And that occurs because of, the violent interactions inside of the earth. You got molten lava, you got molten metals banging around, it comes to the surface somehow or another, you got, a natural magnet. Most of the magnets that you interact with are not natural magnets, they're man-made. Okay, so your refrigerator magnet, they didn't just pull that out of the ground, glue it to the back of something cute, and you put it on your refrigerator. So lodestones are, they're kind of hard to dig up, hard to collect in any quantity that would give you a decent magnet. So most of the magnets that you see, I think there's one on that board over there. Yeah. Looks like a magnet anyway. Well, these things are magnetic. So whatever's in there, it's a man-made magnet. This is not magnet. You can tell the difference just by the weight of them. This thing weighs almost nothing. This has got a little bit of heft to it. So it's got a magnet in it. And they're man-made magnets, I can all but guarantee it. So you have permanent magnets. Permanent magnets. And then off of that, you have man-made. Okay. So how we make magnets in a lot of cases is we can take And we make man-made magnet like what we talked about before, mess up your screws and your screwdriver bits. You've made a magnet essentially. So that would be an example, but we can also take some not non-magnetic, but less magnetic materials, combine them in an alloy and create very strong magnets. That's what most of your man-made magnets are. They didn't just take a piece of metal and beat on it to create this. It's some sort of alloy. It's probably cobalt and aluminum and some other materials inside of it combined together to create a magnet. Okay, so man-made. Permanent magnets, man-made. The characteristic of that is, and they can be natural as well. Obviously, if they're man-made, it can be natural. So characteristic of a permanent magnet is that they can't be turned off. So you've created magnetism in your screwdriver bit. Theoretically, if you just grind on more and more screw heads, you could theoretically lose that magnetism. It's unlikely, very unlikely. So you can't lose the magnetism if you've created a man-made magnet. So you can't turn them off. And the other one is temporary. Okay, so you got permanent and impermanent, you got natural and man-made. And in temporary, you have they can be turned off. Ever been in a hospital when the fire alarm's gone off? What happens to the doors? Shut. What holds them open? It's electromagnet. Right? You ever seen they YouTube videos all over the place, but they have these things that will shred entire cars, right? So what it looks like is kind of like a wood chipper, but it moves really, really slow, and they can feed anything into this thing and it'll eat it, right? But in order to get it in there, you have to pick the car up to put it in there. And one of two ways that they're going to do that. One's with a claw, and they pick it up. But the other is they've got this great big plate looking thing. And what they do is they take that plate looking thing off of a crane and they stick it on top of the car, and magically it just lifts and it gets it where they want it to go, and they just drop it. But nothing grabs it. And what they're using there is an electromagnet. Okay, so anytime I take an electron and send it down a wire, what do I create? Heat. And because I've got a charged particle in motion, magnetism, right? So what if I take two of them and I put them close together? Makes it stronger, right? So if I take a whole bunch of them, put them all together, I can make a very strong magnet, or pretty strong magnetic field, right? So let's shift back to natural magnets and man-made magnets. So let's say I've got a pretty strong man-made magnet. So it's about yay big. And I bring another one that's equally strong and I put it right next to it in orientation. They don't push each other apart. What do I have if I take two strong magnets and put them together?
Really strong magnet.
Bigger, stronger magnet. Okay? So there is a way that we can take this relatively strong magnetic field and make it even stronger. And that is, and this is kind of getting into Friday's lecture, but that is to take it and pull it around like that. Okay? So with this, what we've got is magnetic field. So we have magnetic field lines reaching out like that. But if I pull the wire and I run all these electrons, first off, how many more electrons can I stick on that pulled wire than I can on this flat wire? In a word, a lot, right? So now we've got a lot of electrons creating, this magnetic field, but we've also got the magnets. We got these work like individual magnets. So that's one magnet. That's one. That's one. That's one. That's one. So that would be kind of equivalent to that's one, that's one, that's one, that's one. What did I do? Created a bigger, stronger magnet. Okay, that's how electromagnets work, is you take a flat wire, you coil it up really tight, and that I will bring down on Friday. You pull it up really tight and you run an alternating current through it, and I'll talk about the significance of that. We're going to create a magnetic field in that coiled wire that's very, very strong. It's capable of picking up a car and dropping it into a shredder. Okay? So I turn this thing on and I can pick up the car. Right? But I got to let go of the car somehow or another. If I had a permanent magnet, what am I doing to let go of the car? Right? But if I have electromagnet, what do I got to do? Flip a switch and magnetism goes away and it just drops in the shred. Okay, so the distinguishing characteristic of a temporary magnet is this, that it can be turned off. All right. Even if a blacksmith hammer, you can beat it back into not being magnetic, we're still going to call that a permanent magnet. Okay, because you can't predictably turn it off. What you got?
So, which one is that is the more
Electromagnet. Yeah, they can theoretically make a MRI out of a permanent magnet. The problem with a permanent magnet is that it would be strong enough for MRIs. It would be massive and weigh a lot. It just wouldn't be practical. So electromagnets much easier. Plus, if here's something for you to look up, is look up MRI accidents. All right, so you get close to an MRI and with a maybe a patient's bed that's not made from something that doesn't have strong attraction to, to magnetism, it'll suck it in. All right. Very important. Y'all remember that little bit of information I gave you probably in orientation about, MRI safety? That's a real thing. All right. So if you go back into MRI, make sure that you're wearing stuff that is not going to be drawn into the magnet. If you're wearing your name tag, that little metal clip, it'll pull it away from you. If you're standing at the door, you're probably not going to notice it. But the closer you get to the magnet, it'll start pulling it. Okay? Very, very strong magnet. If you've got your watch on, it'll turn it off permanently. It will turn it off. So if you've got your credit cards in your pocket, what do your credit cards work off of? Magnetism. Magnetism, or that little computer chip. It'll kill your credit cards or your debit cards or whatever cards you have. Okay, if you got a pen in your pocket and it's got metal in it, it'll pull it out of your pocket. People have died in MRI because people pulled stuff into the room close to the magnet and they didn't know that it was magnetic. Oxygen bottles kill people dead, right? So if we have stuff in MRI, it has to be something that's not made out of iron. Oxygen bottles, things like that, have to be made out of aluminum, something like that. Okay.
So is electromagnetic the only temporary one?
Well, yeah, temporary electromagnet turned on and off. Yeah. So the only temporary magnet will be electromagnet. Okay. All right. Any questions on that before we get into our types of material? Okay, so then where we are is on page 81. We have essentially 4 different types of material. The first one just non-magnetic, and that will be something like glass, something that has no attraction, no repulsion to magnetism. And really, of the 4, there's only one that we can observe and demonstrate without, some sort of very strong magnetic field. So we've got non-magnetic, right? No observance of magnetic field whatsoever. And then we've got diamagnetic. And with diamagnetic, what we have is a weak repulsion. Okay. So now this gets kind of difficult to wrap your mind around because, we just talked about hydrogen being two of three parts of two hydrogen, one oxygen, we create water, right? But diamagnetic material is weakly repulsed. Then how does MRI work off of the hydrogen? I don't know. I don't know. Don't know, don't care, don't need to know. So I'm not going to dig it up, not going to test you over it. All right. So that's diamagnetic. It's got a weak repulsion. So water is an example. Ferromagnetic is where we really live. Ferromagnetic material is something like your iron. With iron, what we get is a strong interaction, and the iron directs the lines of magnetism, grabs onto them, directs them, the iron becomes magnetic. So you got susceptibility, you got permeability, it becomes magnetic, strong attraction. And then we've got paramagnetic material. And paramagnetic material has a very weak attraction. A example of paramagnetic material would be aluminum. I think this is aluminum. So we tend to think of aluminum as being non-magnetic because you stick a magnet to aluminum, and what happens to it? Falls off, right? See if this is aluminum. It is. All right. The board obviously has some iron in it or something, but this tray down here, nothing. It just falls. Okay. You can demonstrate some, I won't say attractiveness because it's really hard to demonstrate the attractiveness, but you can demonstrate that aluminum is affected by magnetism back in the MRI magnet. Okay, probably the most, probably the most impressive display I ever saw of magnetic field strength was in MRI, obviously, but the direct witnessing of it was that there was a guy, his name was Fred Bussell. I don't know where he is now, but brilliant guy, really great. And most of the MRI techs in the Tyler area for probably 15 years were directly or indirectly trained by Fred Bussell. We tried to get him over here to teach MRI for us, and we thought we had him, and he kind of got away from us. So what he had was a piece of aluminum about the size of this notebook. Okay, aluminum that size is, it's kind of heavy, but it's not all that heavy. It probably weighed about 10 pounds. So we had a piece of aluminum about this big, and I was a first semester student, and we were doing an MRI, just a tour of MRI, and he was telling us how it worked. So we walk in, and he takes this piece of aluminum, and he puts it right at the opening of the magnet. Right? If it was CT, we call that a gantry. It's gonna be kind of loud. Not far off the floor, but that's all right. I want this up here. So what he did was he took this thing and he stuck it right in the end of the magnet. It had a hair in it. It's not mine. So he stood it up like that, and it stood on end. All right. So he's describing the magnet, and he's telling us the properties of the magnet and how MRI worked. And just almost without thinking about it, he reached over and knocked it over. How fast did that fall? Quick, pretty quick, right? So it went from standing on end to laying flat, half second, tops, right? This thing took about 4 seconds to fall. And it looked like an optical illusion. You would expect 10 pounds of aluminum to go down hard and make noise, right? It went down so slow, it made no sound whenever it hit, and it took a long time for it to fall because the magnetic field lines are so thick running through that magnet, and the aluminum has paramagnetic properties. There is such a small attraction that that strong of a magnet can demonstrate that attraction in MRI. Here, that magnet's not strong enough, right? It just completely ignores it. But if that magnet was strong enough, it potentially could have some sort of attraction to that aluminum tray there. All right, so non-magnetic. And we've got diamagnetic, weak repulsion, paramagnetic, weak attraction, and ferromagnetic is where we're going to live on Friday. Very strong attraction. We're going to talk about that and how we use magnetism, how we use alternating current, how we use ferromagnetic material to create a really strong magnet. Our purpose is not magnetism, but that's essentially what we're creating so that we can increase and decrease kVp, increase and decrease mass. Okay. So let me make sure. Oh, yeah. Before, I know that sounded like a wrap up, and it kind of was supposed to be, but then there was something else I needed to make sure I brought up. All right, so magnetic laws, very similar to laws of electricity. What were our laws of electricity?
It's, the rest of that.
Yeah, opposites and the rest of that. Yeah,
Oh, sorry.
yeah. But you started strong.
One word.
Opposites attract, right? So you take the north end of a magnet and you put it towards the south end of a magnet. And what do you get? A longer magnet, right? So you take the north end of a magnet and you put it towards the north end of a magnet. And what do you get? Repulsion. So you get attraction and repulsion, right? So that's number one, attraction and repulsion. So you got that, but then you've got, let's say you've got a north end of a magnet here, you got a south end of a magnet here. I get them close enough together, and what's going to happen, even if they don't touch, even if I don't make them touch, what's going to happen? They're going to pull each other together. They're going to snap together, right? Because of attraction, right? So what if I have two very weak magnets? I mean, if you were to take a refrigerator magnet, they're really a pathetic magnet, and let's say you've got the magnetic side here, and the decorative side here. Talk about pathetic. That doesn't even right. Okay, here. Decorative side here, and I took a second magnet and I put it directly on top of that. Would they stick together? Probably not. Just they're weak, very weak magnets. Okay. So what if I remove that? I put them together. What would I have? They'd stick together and probably make a stronger magnet. Okay. So going back to electrons, how did we get a stronger electrostatic charge? Add more electrons. Okay, so when we have one electron flowing through a circuit, what do we create? Heat. Heat and magnetism. I'll put two of them on there. What do I get? More heat and more magnetism, right? So and each one of those is going to create a certain amount of magnetism. The more magnetic domains we put together, the stronger the magnet. Okay, that's number one. Now we take these, and even though they're strong magnets and I put them further apart, what's going to happen to them? Are they going to be attracted to each other?
Yes.
Yes, but not enough to pull them together, right? So what happened there? Did the magnets just get weaker?
No, the distance.
The distance. So what was Coulomb's law? The more you have, the more you have. Closer they are, the more you have, right? We're just going to recycle Coulomb's law here. We're not going to call it Coulomb's law, but it's essentially the same thing. The more magnetic domains that you have, the stronger the magnetic field. That's number one. And number two, the magnetic field is going to be inversely proportional to the square of the distance between those magnetic moments. You spread them out, You still got your magnetism, but you don't get that bigger, stronger magnet, right? You put them together, you got a bigger, stronger magnet. The more you have, the more you have. The closer they are, the more you have. Just like your electrostatic laws. Okay? Just Coulomb's law all over again. Any questions? What you got?
Are they put more together and they stronger?
Yeah.
I don't know if I got confused because earlier it didn't say that it's like they'll just pair together and cancel each other out.
In the atomic structure they were.
Okay, but
But-
not, okay.
Yeah, but when we just have electrons traveling down through a circuit, yeah, the more we have, the more. Yeah. Anything else? Pick up